Okay, we can start. Thank you. We have the green flag to start this session. So thank you to the 100 participants that we have already, and to the panelists, and also to Jim and Stavula for putting together this session on AI for networking and networking for AI. So before I thank the panelists and I introduce them, let me give a little bit more of context. Okay, when I wanted to do that, my initial idea was a little bit different, and as usual, Jim acts as a moderator on me. The title that I had was something like, "Is ML for networking a hype, or do we really need ML in networking?" Okay. And Jim said, let's make it a little bit more constructive and discuss where ML is useful in networking, and where networking is useful in ML. Okay, because both are related and are important. So that's why you have this panel today. I'm still interested in I mean, I'm always frustrated by research topics that I call solution in search of problem. Okay, I'm sure ML is not a solution in search of problem in networking, but some researchers tend to jump on everything and make it a solution in search of problem. I'm not going to mention the very popular blockchain that everyone here will relate to a solution in search of problem. Many people will disagree with me too, and it's fine. Okay. So that's why we have brought together. Oh, where are the slides? Nobody's sharing them. Sorry.
I think that's your job to share them, Christophe.
Yeah. But you know, people ask me to work with suboptimal tool like Zoom when I'm used to Meet. So no, I'm not paid to say that. I mean, kind of. Can you see my screen?
We can.
Can you see the slide? So this is my introduction explains why we have such a diverse panel of people working on ML for networking and networking for ML. So we are very happy to have Kyunghan Lee. And please forgive for the pronunciation. I'm terrible in English and even worse in Korean, probably. Who is a professor at Seoul National University. Each of them will have 5 minutes to introduce them. Okay, so I don't need to do that. Michael Schapira from University of Jerusalem. I mean, thanks to both of you, and my thank is proportional to the time difference you have with the epicenter of this networking channel. Okay. So
I'm actually in Denver. So you shouldn't be that.
So that's a good one. But Kyunghan is in Korea right now, so it's probably around midnight. So Ness is in Ohio, so not too far from the epicenter, and same for Noah. Ness Shroff is a professor at Ohio State, and Noah Zilberman is a professor at Oxford. Okay. So the two organizers, Jim and I mean, usual suspect, you have seen us many times. We are very honored to host this panel, and I think it's time to start with the useful content.
So, Christophe, just one thing about logistics and questions. So I think we're up to 130 people now. There are multiple ways you can ask questions. There's a Q&A. If you look at the bottom of your Zoom screen, there's a Q&A where things will get queued up. And there's also a chat feature as well. And this conversation will continue afterwards on our networking channel Slack. And so there are multiple ways to ask questions, both live and continue the conversation afterwards. So if you've got questions, please, or comments you'd like to make, please type them into the Q&A. In particular, that's a good place to put them. And then as we go along, Christophe and I as moderators will sort of moderate and ask your questions pose your questions to the panelists. Okay, so I think we're ready to get started. Why don't we just go in alphabetical order? I think our panelists are going to start with sort of a 5-minute position statement and a bit about themselves and their work and their ideas on this great topic. So Kyunghan, you want to go first?
Yeah. I have like 2-page slide to share. Can you see this? Yeah. I have been working on the 6G designing the task in Korea. And within the 6G, as I find, there are very interesting AI for networking and networking for AI problems. And I believe my ideas and the problem statements are going to be well matching with this like a panel topic. So when I was first challenged with the Korean people that who are complaining about the difference between 4G and 5G, I kind of had to give them a hope that the 6G would be completely different in terms of like application performance and enabling the futuristic services such as the real-time AI ML analytics or computing over the network, such as using ChatGPT over the network, or XL, the extended reality, or the metaverse. I had to give them some kind of like a hope. And I had to also find the reason why the 6G network is indispensable compared to other ways of enjoying our computing capability. So I can classify the multiple devices in like 3 types, and type 1 is the most popular smartphone or the smart glasses type of the devices, and type 2 devices are like vehicles, so they are very powerful. And type 0 devices, we don't have it yet, but it's going to come soon, right? So the Neuralink is implementing such a thing. So when we try to implement all kind of these futuristic services, I kind of devise a term like a connected computing, which should be giving application performance, which is completely indistinguishable from running the thing on device. So what we have found is in the case of type 1 device, actually, we cannot increase the performance of these devices sufficiently to provide such the futuristic services, because currently the Morse law is still working, but the Dennard scaling, which already came to an end by 2012, we cannot actually anticipate a good performance in mobile device with the limited power consumption. So with this like thermal and battery capacity limitations, we cannot actually provide such a beautiful, powerful services to the users over the net. So the over the network computing, like a connected computing, is kind of needed to provide such a beautiful services. And I guess that's the indispensability of 6G networking. So the key question would be, how can a network enable seamless connected computing, which is indistinguishable from on-device computing? And I kind of posed a connected computing reference service model. And this one, which is delivering the sense data from the mobile device to the network and get the process result within this time budget that the application or the user allows. So this job completion time, which is nothing but just a summation of encoding, decoding of the data, and the uplink transmission and the downlink transmission and computation in the solver, and also the encoding and decoding for the downlink reverse direction. If all the summation can be within this time budget, then yeah, we can call that's a beautiful connected computing setup. And I find there are 2 real challenges that should be addressed by this neural network or the AI ML techniques. The first one is about the reducing the transmission time, because the transmission time is going to be the key for the performance degrading factor in this type of connected computing. So the neural compression, which should go beyond what we have currently with all kinds of engineered codec, And another one is to enable some kind of active networking concept with this like a neural, the radio resource management, meaning that whatever you want to transmit over the network with different size of the application data, it should be transmitted in time to the server or to the device in return. And then must be done with the proper allocation of the radio resources. And that is nothing but just the ILP, the combinatorial problem. And there is no good solution. I guess the neural approach would be a very energy efficient way to run this. And the situations are getting better and better to run this within the base station. So yes, these are good directions of utilizing neural networks for neural network services in network. Okay.
Okay, thanks very much. Michael?
Yeah, hi everyone. So thanks for inviting me and thanks for attending. I'm here as a representative of the machine learning for networking direction. So using ideas and machinery from machine learning to address classical networking challenges. And I think maybe I'll start by saying that I think it's a very interesting time to be in this area, precisely because of what Christophe said before, because it's not clear yet whether we see other areas of computer science that have been completely overrun by machine learning. You no longer meet a computer vision researcher who isn't actually an applied machine learning researcher. And it's not clear whether we're, the dinosaurs waiting to be hit by the asteroid here, or whether, as Christophe said, this might be a solution in search of a problem and we're throwing reinforcement learning or whatever at every problem we've ever seen in networking research. And I'm pretty sure that the answer is somewhere in between, but the fact that we don't know what the answer is makes it a very fascinating time to be in. And actually, this is one direction I'm pursuing, which is trying to figure out what the killer apps for machine learning are. And one thing, and this was actually one of the questions posed on the panel description, right? Well, what kind of problems are amenable to a machine learning approach? And my argument is that the most natural place to apply machine learning at this point is where we're already at least implicitly applying machine learning, maybe badly, but applying machine learning, meaning we're predicting something from data. And there's a lot of examples. You're doing traffic engineering based on predicted future traffic demands. When you're doing congestion control, you're trying to predict, at least implicitly, but sometimes even explicitly, the bottleneck bandwidth or the latency of the network. In video streaming, you're making decisions based on predicted download times of video chunks, right? So I think there, the question isn't so much, should we be data-driven, right? Should we be predicting something? It's the question of how we should be doing that. And I think that opens up a lot of algorithmic possibilities. And another thing that I argue is that we can't just hurl machine learning techniques, the abstract ones, the general ones at the problem. There should always be some structure in the problem itself that we're leveraging. And I think that comes into play in a lot of different contexts. And we're seeing that again and again, where something might work well in simulation, but in the real world collapses because we haven't figured out exactly what the problem was initially. So I've been working quite a bit along these lines, looking at problems like video streaming and traffic engineering and congestion control, which I've mentioned. And I think that there's promising directions, but I think we're very far from a definite answer to the original question. Another direction that I'm actively pursuing that I think is also a contribution to machine learning in a sense, right, is safety. Right? I think that it's one thing if your machine learning based algorithm fails to recommend the right movie, unless it recommends something extremely offensive to you, right? It's not that horrible, right? But when you're trying to deploy something that's mission critical, right, or that could hugely influence quality of experience for a lot of users, safety comes into play. And this is coupled with the fact that a lot of when you're deploying things on top of the internet, there's no way your finite training data reflects the actual broad diversity of environments you'll be operating in. So I think there's a lot to be done in terms of formal verification of machine learning and how do you default online to some safe policy when things start to seem bizarre. Yeah, looking forward to brainstorming.
Great. Ness, you're muted.
I'm muted, yes. Thanks. Yeah, so let me try to sort of address the first part of the first question more broadly. I think, Michael already hit upon some of the points that I wanted to make, but what I will try to do is, try to provide some example conditions which are very much prevalent in networking for which machine learning would be useful and result in potentially much better performance than traditional approaches. For example, network optimization, network control, etc. So one, such area clearly is when there is a significant amount of uncertainty in the system. And the good news is that networking has many, many scenarios in which you have a significant amount of uncertainty in the system, a significant amount of imperfect information being need to be information need to be predicted through imperfect information that you have. For example, if the channel conditions are not known or can't be easily estimated, user dynamics might be unknown, same with mobility patterns, then we can develop appropriate machine learning techniques such as online learning, online reinforcement learning for decision making, where you have imperfect or unknown information in order to optimize various operating objectives. Another area where machine learning is also useful is really in uncovering these very implicit relationships that we have in this complex system. For example, one area where I've used it is in determining the impact across multiple layers from the edge to the core in caching problems, and then updating, edge caching decisions accordingly. One more area where I think machine learning is quite natural and useful is when the problems being solved are too complex, where the objective is very, very complex. You might have non-convexity, you might have multiple objectives, or the feedback is no longer scalar. For example, the feedback might be application dependent in making decisions. Now, sort of getting to the second part of the first question, I'm going to be a little bit provocative in the line of Christophe, and which is I'm going to say that I simply don't believe that applying traditional ML approaches to network problems in a sort of a black box way without sort of digging into the network problems and developing solutions for them is a good approach, even though it appears to be fashionable to do nowadays, even in the top conferences. And the reason I believe this very strongly is because networks are inherently complex beasts, and we really need solutions to take into account their very special structure, their very special dynamics, their very special constraints, be those non-stationarity, hard constraints, heterogeneity, geographical context, etc. So we need solutions that build on the structure of these problems and also don't disregard the domain knowledge that we have built up in these areas over the decades. So these are things that I have myself tried to take into account into problems that I have investigated from developing online learning techniques for edge caching, as I mentioned earlier, beam alignment to constrained reinforcement learning problems for various network control problems, to meta learning to accelerate training times, etc. The point that I want to convey is that this is hard to do because oftentimes these solutions need new foundational advances in machine learning, either substantial modifications of existing approaches or completely new solutions. But the good news is that once you've developed these foundational techniques, they can not only be applied to the networking problem, but as has historically happened, can also then be applied to other domains. I'll give one example. Our recent RL work under safety constraints, which are hard constraints, is not only applicable to network control problems, but can be applied to other sort of safe RL problems, safe driving systems, etc. I know I'm running out of time, so I'll be very quick regarding the other two questions. So the second question was regarding access to data. This is absolutely a challenge in validating models for networking systems. So I forgot to mention that I'm leading one of the NSF AI institutes on developing XG edge networks as well as distributed intelligence. And in our AI institute, we have a number of researchers who are collecting data sets, and we have built a repository that's accessible to everyone, where we are generating and collecting not only data sets, but also generating software APIs for Wi-Fi, LoRa, cellular, LTE, 5G, etc. Having said that, I should point out one of the problems that we have in networking with data. So unlike traditional classification problems, where you can use data sets very easily for validations, because the data being generated oftentimes in networking areas is also dependent on the control mechanisms that we design for the networks themselves. In addition to these data sets, we also need easy access to large test beds. And this is a very important part of any research that you're doing on ML for networks. The final question was about
Ness. How about if we cue any final questions and we can come back to that data one, because your comments raise way more questions than they've answered, and it's a rich area we can come back to.
Sure.
And turn things to Noah, and then we can come back with general questions, because I think I'm seeing a number of questions already in chat and also in the Q&A.
Wonderful.
Sound good? Okay. So Noah.
Yes,
thanks.
Thank you. And thank you for inviting me. So I'm on the networking for AI side. And I think that actually, as a networking researcher, this is very exciting because all distributed ML goes through the network. We have huge amount of data that goes through the network wherever you are doing training. It takes a significant time of the training. It brings up new opportunities if you'd like to look at accelerating training framework, at accelerating inference, at measurements of network traffic, because machine learning traffic has very particular patterns. And that's also why there's increasing research in the use of optical networking for training. But I want to focus right now on the incentive to move more machine learning into the network itself. And specifically, I'd like to refer to 3 benefits of offloading more machine learning into the network. I refer to those as the 3 Ls: location, latency, and load. First, for location, every data that is generated goes through the network. For the data to get from the user to the cloud, it goes through the network. If you are pulling from a storage, it goes through the network. So everything goes through the network, and the network is also very close to the user, which brings me to the second L, to the latency. If you can act on the data as soon as it arrives to you, then you can reduce latency. You can operate on the data at the edge. It doesn't need to get all the way to the cloud. And also that supports use cases that are latency sensitive to reduce the round trip time. And the last one is the load. And when we are thinking about the load, we need to remember what is the processing rate of network devices today. We are talking about billions of messages per second that are being processed. Now, if you can do billions of operations within the network, even if these are not complex operations, these operations are offloaded from the server. So we are also releasing a lot of cycles from the CPU. And I'd say that there are two types of accelerating machine learning within the network. One of them is what I refer to as network-assisted machine learning, as one as in-network machine learning. Network-assisted machine learning basically means that the network provides a service such as gradient aggregation to accelerate a traditional machine learning framework that are still running on a server, that are still running on a GPU or other accelerators. But the network provides some part of the acceleration because it acts on the data as it goes through it. In-network machine learning means that the machine learning itself happens within the network, and that is typically inference. And for that, if you are looking at the network devices, and I mean switches or routers, network devices are resource constrained. So we are looking at a resource constrained machine learning problem. And there's a lot of work that has been done in this area already. There have been more than a dozen machine learning algorithms that have been mapped to run on commodity network devices. So for example, on Tofino switches, a lot of work that has been done on SmartNICs, on FPGAs, and that has shown these benefits in latency and in reducing load. The number of applications that have been demonstrated so far has been somewhat limited. Mostly we are talking about applications in traffic classification, in cybersecurity, anomaly detection, for example, but also in time-sensitive applications such as algorithmic trading. And developing more applications that are in-network machine learning applications are actually a great opportunity in my mind. And with that, I return the ball to you, Jim.
Okay, great. Wow. Thanks for those, those opening statements. And I don't know, I wrote 7 questions just of my own for discussion, and there's a whole bunch more that have shown up. So please, again, everybody use that Q&A tab to enter them. And maybe we could just start off with a question that a couple of people have asked in from slightly different angles, and that has to do with the safety issue that Michael brought up and Ness talked about. And so both Gerard Lalande and Edmundo Souza Silva brought up this question about, well, first of all, we have black box approaches, right? And if we need safety, what does that mean, especially say in light of adversarial AI and who knows what things have been trained on, and all the ways one might attack a machine learning algorithm that's operating sort of in live and online. And so I guess maybe a question is maybe just to expand a little bit on the issue of safety for mission and life critical systems, especially in light of a lot of the concerns more broadly, I think, across AI and ML about safety, explainability, things like that. And we'll just open it up. Why don't you all just unmute, all the panelists just unmute your mics and just start talking.
So Jim, I can start with a stab at the question. So the first thing that I would probably say is that safety is a very, very big area. And we have to be careful about how, what we mean by it and how we define it and what the scope of safety really is. So, for example, at the moment, forget about adversarial attacks, all right? Forget about data poisoning and all of that stuff. We still don't have a good handle on how to address safety in complex system scenarios, such as self-driving, etc. Even if you did not have all of that, right? So because developing solutions, whether they be for reinforcement learning or otherwise, that meet hard constraints when you may not even know the constraint set, for example, is not easy. This is a very hard problem in and of itself. So that's kind of step one that needs to be addressed. Then you need to address, some of the issues that you pointed out, where potentially you might have jamming that might occur in safety critical systems, where somebody's intentionally, trying to cause a problem. Or there might be data poisoning that might happen in, say, large-scale control systems that needs to be addressed. So I would say there are many, many layers to the safety problem. And at the moment, we are still sort of dealing with, each of these independently. And the key challenge will be, how does one integrate all these solutions to come up with an overall comprehensive solution? And I'll leave it at that and let the others take over.
Yeah, I can continue maybe that. I fully agree with Ness that the problem of safety, right, needs to be well defined. And even when we're ignoring the adversarial element of safety, there's still the classical question of generalization. Right? We are training every database system in some environment. We can hardly expect it to work well when the operational environment greatly deviates from that environment. And in networking, this is a very pressing problem because there's such a daunting breadth of network environments and application domains and traffic conditions and failure scenarios, right, that we want our systems to operate well in, that I believe personally that without safety nets in place, right, it's going to be very hard to deploy whatever solution we come with if it's actually largely dependent on data it has seen in training. And I think that there's various interesting directions that people have been pursuing. One is robustifying the training process itself, right? It's how do I introduce challenging examples into the training process so as to, try to make the system as robust as possible, right? But even if I did, right, there's naturally, I can't hope to capture the variability of real world conditions in its entirety. Which brings us to questions like, what can I formally verify before actually deploying the system, right? For traditional software, we have software acceptance tests. What do we have for machine learning-based systems? And I think that is where formal verification and advances we've seen in that area could be very helpful. And one thing I would like to note is, networking is not only a new set of problems, it's also new opportunities, I think, for machine learning. For example, the size of neural networks that we deal with is many orders of magnitude smaller than what people typically encounter in computer vision. That gives rise to a lot of, say, formal verification approaches that one simply couldn't apply in other domains. And another thing that I think is interesting in this context is, which is also an opportunity, in networking, there's always the default system, right? Typically, people don't have that in machine learning, right? But we know that if I have a reinforcement learning-based congestion controller, I could always default to TCP cubic, right? If things start to seem bizarre, there's always the system that has been tested in battle, right? That may not be optimal, but it's fairly safe, right? As evidenced by many years of deployment. And I think that a super interesting problem is, how do we know in real time when to default? Right, where the reason that this is challenging is because it's not just a question of, am I performing badly? Maybe I'm performing badly for objective reasons, right? Maybe the network is challenging at this point in time, right? It's a question of, could I be performing better, right? Which is a hard question conceptually to address. So I think that people have been targeting this from many different directions, and I think that we have yet to converge to the right set of solutions, but there's many complementary angles that I think are interesting.
Okay, there's a couple of questions that have come up now, more on the networking for AI that I want to get to in just a second. But Michael, you brought up the question that or you brought up the issue that there are formal verification techniques and that one might apply here, looking at this more from a safety point of view. And that sort of gets to a question that somebody had asked in the chat about where people are publishing this work. Where would you, so if you're interested in verification and safety of ML control in networking, you could go to a bazillion networking conferences, programming language conferences, verification conferences, software engineering conferences. So let me ask you specifically for safety, and then more generally, I'll ask everybody, are there background books? If somebody wanted to learn more about AI and networking, where would they go? And for this particular important issue of safety, where do you see these kinds of things, or are they just everywhere?
Where do I see them in what sense?
Oh, sorry. Where do you see them in venues? So if this,
I see.
where does that community, where is that community that's working on those problems?
So relating, maybe the other panelists have better ideas regarding books that are in particular about systems and machine learning. I think they have yet to be written. Because I think we're still at very early stages of this area in general, and we haven't yet converged to canonical textbooks, which I think would be a much more mature stage than we're at now. In terms of venues, I think that this is history repeating itself to some extent, right? At some point in time, when SDN became a thing, right, we started seeing programming languages for SDN, or verification of networks, right, for SDN, or suddenly distributed computing approaches to time synchronization in the context of networks. And I expect that we'll see this type of work at different venues of different communities, depending on what the key innovation is. If you're using networking as an example, right, for a general verification technique or a general a machine learning technique, and right, then maybe that's more appropriate in one of these venues. But in a lot of cases, I think the networking community should be open to publications that maybe use even ideas that are well known in another community, but have to be adapted in clever ways to address a pressing networking challenge. So I expect this to be, before we converge to some sort of venue that everyone publishes in, I expect there to be some turmoil.
Okay.
So regarding the safe learning and safe control, especially with the reinforcement learning, I completely agree with Michael, and because I have worked on designing the TCP problem, the low latency TCP with learning-based control. Most of the cases when we are facing networking problems, we see those problems should be addressed in real time or near real time. And that gives a lot of pressure, because most of the cases in machine learning domain, they're addressing these problems of facing unseen scenarios or unexplored scenarios by giving them more time to explore the situations and learn and accumulate the knowledge. But in most of the cases, what we are dealing with in networking is to handle the problem nearly immediately with the baseline of the performance of what we can achieve with the engineered solutions. As Michael mentioned, maybe we can use some kind of fallback mechanism, but there must be a way to distinguish whether this situation is completely unseen or recorded situation in the previous history. So there must be a very good technique of distinguishing whether this is a new situation or experienced situation. And of course, there must be a way to enable some kind of predictive control. At the moment, we are facing some kind of unexperienced situation. How can we design such a predictive design a predictive model that can give almost immediate solution, which is performing as good as at least engineer solution? I guess that's one of the key challenges we have to address in network, the learning-based control problems.
So to go back to the question of where can you find the material, I'm sorry to disappoint you, but it's going to be on archive. Machine learning is moving so fast that the material will be first probably on archive, and then the paper will be published a year or two later in a conference or a journal. We are just too slow with our conferences and formal publications. Everything goes on archive. If you are talking with anyone that is doing ML from the more ML communities, that everything is on archive. They are not waiting for it. And we had a paper that was about trustworthy development of AI systems that was first on archive, then a year later it was on Science. But it's just
okay.
late.
I'm not going to ask you the question, Noah. I have another question I wanted to ask you, but I'm not going to ask you the question about, you said everything's on archive, and that's true. How do you find what you really want that's good there? So that's the question I'm not going to ask you. The question that I do want to pose to you is actually one that that comes from Dirk Kritcher, and Christophe mentioned we should give priority to people who are in distant time zones. So as I recall, he's in Hong Kong. So he's like Kyunghan in that he gets priority because he's up late. And let me read you his question. In networking for ML, and I think this both addresses what you had been talking about, Noah, and also Kyunghan. He says, so for networking for ML, and then you think about some of the requirements for real time, for example, or some of the issues that you brought up about where computation happens. In his opinion, one of the interesting questions is the design of appropriate networking and distributed computing abstractions that sort of apply to this, the use of ML in network systems, but also that also includes a robust security model. And maybe I could add on to that. Noah, you were talking about offloading to attached devices or running in NICs. But then you also mentioned about, well, we could do things in clouds also. So, I mean, there's computing sort of layered all the way across from one end of, from the edge device all the way deep into the network and, in network and in network interfaces and things like that. So maybe one of the two of you or both of you or everybody could comment on this notion of abstractions and architecture for this larger issue of ML-based control.
This is a question where you need to consider what is the use case, because you need to design for it from the edge device all the way to the cloud, and to take into consideration what are the capability of the devices. So for example, if we are talking about the security issue, I'm not suggesting that you'll be doing encryption decryption within the switch, but for example, if you are using a smart NIC, a DPU, an IPU that has an IPsec accelerator, and you have the ARM cores that are running Linux, then you can basically do a lot of what you normally do on a server. And you're still saving your PCIe latency, and you're still offloading from the CPU. If you are thinking about an IoT gateway is CPU-based. So it's not significantly different than your standard machine learning model, but it's a different functionality that is located in a different place, possibly, at the user site, maybe on a smart manufacturing floor, maybe we are thinking about roadside units for autonomous vehicles. These are places where you will have devices that will be significantly resource constrained, but may not necessarily have a completely different processing architecture than what you'd be familiar with.
Mm-hmm.
Yeah. So in the internet, this is so much disputed. So I cannot think of any good place to run such a centralized intelligence repository. But in case of Seoul network, in the Open RAN activity, there is a concept of service management and orchestration function, which is taking care of all the performances over the network and the computing. So it is going to handle basically all the problems collected from the users and the base stations and all these core network devices. And hopefully that can have one centralized, very good, powerful version of the knowledge repository, which is evolving as we have seen in the case of like a continual learning with the concept of this like a safety awareness. Not quite sure how we can design some very good solution for this like a fully distributed internet case.
So Kyunghan, what I hear you saying when you talk about Open RAN, you're talking about things happening, the knowledge repository that you talked about happening very close to the edge, right? And in the case of as not the case in an Open RAN, but in the case of a lot of RANs, that also means that you're running sort of in a single operator's network and potentially with proprietary information and things like that. So I just want to make sure I understand, is what you're talking about really the locus of computation really happening really far out at the edge, as opposed to, I don't know, back in an Azure cloud, sort of deep in a data center somewhere?
Yeah, no, actually, that's not the case. I was talking about the case of the 6G where the time critical services are really important. And in that case, you have to really carefully manage the time for computing and networking. So you don't need to use, I guess, the far away clouds in the services.
Okay.
Yeah, I sort of just want to go back to what Noah said. I think a lot depends on the use case. So for example, it may not be appropriate for real-time services to train something in real time if, for example, the response time that's needed is on the order of milliseconds, right? Because that's very, very hard to do, right? So it depends again on what you are doing in terms of your of your problem that you're trying to solve. So if it's, for example, real-time control, then you may want to depend on something that's either pre-trained and then you're kind of making decisions based on some actions that are predefined, or if you're doing something which perhaps doesn't require real-time control, then you may even want to train on a nearby edge device or an edge cloud and get that information to make decisions for the network.
Okay, we've only got about 10 minutes left, and there have been a couple of questions on that have to do with data sets. And Ness, you said something about that in the beginning, and then there's the issue of training, and then the online. We might talk about access to data, who owns the data, is the data proprietary, sharing models that have been trained on data. So let's make the last question something having to do with all things data. And let me just get some of your, have some of you put some of your thoughts out there.
I can go if you'd like.
Well, maybe that was too general a question. The silence is deafening.
Yeah. As I mentioned earlier, I think data is a big issue because it's firstly it's very hard to generate a good amount of real data that can be used and then generalized from for networking systems, because networking systems are so complex, and so we have to do it for various types of functionalities. But even beyond that, if you're solving like a classification problem, there are sort of a set of images or a set of well-defined data sets where you can test your AI algorithms. Oftentimes in networking, the problem is that your algorithms itself are now going to be generating new types of data. And so the data itself changes depending on what algorithm you deploy. And therefore, sort of a static data set may not always work for what you want to do, right? And so for this reason, I think we cannot simply disassociate data sets from experimental platforms. So the point that I'm trying to make is that validation for a large class of networking problems requires an experimental platform, just not static data sets. And I'll be happy to sort of let the systems folks, elaborate more if they'd like. Yeah.
It's actually the data management is a very difficult problem, but recently what people are talking is about the knowledge distillation from multiple teachers to like a one model, or transferring the knowledge from a couple of models to the other model. So if we handle these knowledge extracted from the data in the model level, I guess we have more chances to interwork with the multiple proprietary the data dealers, and they can create some model which has like a common the structure. Then they exchange their the learned information using such as like a knowledge distillation technique or the reverse knowledge distillation techniques, so that we can just share the extracted information without the bothering privacy issues.
Yeah, I think that the ML challenge sort of aggravates a problem that we're already having in some sub areas of networking, right? Where if you want to publish in data centers, if you want to publish on WAN traffic engineering, and you have no access to empirical data, a lot of empirical data, that poses a real barrier for publication. And in the ML world, this is going to be much worse because you need data to train, right? Regardless of the test itself, that for the system to be good, you need huge volumes of data, often more than you needed for the test previously. And I think that one thing we should be doing is try to develop a more data-oriented culture, like the ML one, meaning canonical data sets. It's fine for them, to not capture everything, right? But to sort of give us a starting point for evaluation. And I fully agree with Ness that because of the sequential decision-making nature of a lot of these things, it's static data sets might not suffice. But for a lot of problems, they do suffice, right? And for the ones they don't, maybe we need canonical experimental frameworks. But I think what we're seeing now is a lot of publications sort of talking past each other, in the sense that each one has its own data criteria and data sets and performance criteria. And often it's hard to figure out what the right solution is, because each one is at least implicitly solving a different problem. So I think in that sense, there's a lot to learn from other communities about employing data.
Yeah, I'm really. Oh, go ahead, Noah. Sorry.
Just 1 second. So I'd say that in 1 sentence, what we need is the equivalent of ML perf for networking. So having networking ML perf.
The image analysis community or the video, they have been much better than us, and they have their benchmarks. And I've seen them work on the same pictures or the same set of pictures for 20 years. I mean, maybe we need to do that for ML. I mean, that would help reproducible research, that would help compare the results and so on. But I'm not sure that, as Michael said, this is a cultural problem in our community. Anytime you try to do a benchmark, people criticize it, and people claim that, oh, it's too old, or no, it's not representative. So I've been trying to do benchmarks for anomaly detection for years. Okay, nobody is using them, so we need to change that culture, I think.
Okay, so we've got only about 4 minutes, so we should start wrapping things up. I don't know, anything anybody wants to add in 30 seconds, because we need to sort of close things up. Let me say also, the conversation can and will continue on our Slack, and there's information posted. We're going to take all the questions, lots and lots of questions in Q&A and also from chat, and move them over to Slack. And we hope that all of the panelists and everybody online can participate in that. Okay, so we should probably wrap things up, because I know a lot of people have things scheduled at the beginning of the hour. So I wanted to share my screen here just to wrap things up. That's not what I wanted. That's not what I wanted. Oh, I know. This is a problem that happens when you have to use Google Slides instead of PowerPoint. Okay. Christophe, everybody wanted to thank the panelists again for being here, and just, again, a fabulous discussion, and a discussion that we're gonna be able to continue online in the Slack channel. And so thanks for your time. Thank you, those of you who are in distant time zones, for being here. The last thing we wanted to say is that this is actually the very last session in this spring semester session of the networking channel. So we'll see you again in the fall. It's our last one of the spring right now. And so thanks again. Thanks to these panelists. Thanks to all the speakers and panelists. I mean, it's been a really fabulous year. Stavrula Magalevra has really been behind the scenes doing a ton of organization and technical support. So Stavrula, thanks so much from everybody in the whole community for this. We have a steering committee who've done a great job in helping to choose all these topics, and to the many thousands and thousands and thousands of participants, both live and online, and those who have viewed things after the fact. We do have a questionnaire out. We're sort of interested in what folks might be interested in terms of topics for next year. So you see a quick, there's a URL, but everybody who is online now or has received an invite will get an email. It's a short questionnaire. We really just want to get your thoughts on the networking channel topics, how we can improve things, how we can broaden our reach, things like that. So Christophe, you want to add anything as we close off here?
No, nothing special. Thank you very much. And I hope that the next panel and the next season will be as exciting. And I'm glad to be confirmed in my thinking and opinion about machine learning. That's a special note for Michael.
Okay. So thank you again. Thank you again to our panelists here for this particular session. Thanks everybody for being online, and we'll see you again in the fall. Okay.
Thank you very much.
Bye-bye.
Bye.
Thanks again, folks.
Bye.
Thank you.